How did you not know that you can't talk?
No, it's not that I didn't know you couldn't. We never had one.
I mean, to be fair, like,
It
sequels
never
will
occurred
be
to me.
very, yeah,
It
like,
never occurred to me why I would ever need to control.
yeah, it's kind of a
It doesn't
social
ever
part.
occur to me.
No, it has to be. No, yeah, I can't think of a sequel. Can't think of probably
Presumably, you go down the line in order to do all the same statements.
Okay, so hopefully you can convince each other, at least in the first part, that those four things are all saying that. Some of them in perhaps more obvious ways than others. And along the way, you might even have discovered other ways you could have said them as well. So, for example, we deeply well here have said Q is a subset of P prime. That would also be true. Okay, now, I just wonder, this is quite a bit tougher, this question, but just in case, did anybody come up with any ideas about this? How would you arrange, how would you go about trying to show all of those four things saying the same thing? Any ideas at all? This one is quite well. Any ideas? Okay, I'm not surprised, especially since you didn't have that long for the entire discussion. The main point I want to make here is always to be lazy in the best sense of the word. Always look for the simple way, always look for the way of doing less work rather than more work. That's perfectly respectable. There's nothing honourable about doing more work than you really had to, just for the sake of it. So a mistake would be to take each of these things pair by pair and to say, well, I've got to show that these two are the same, and then I've got to pick all possible pairs and show that they're all the same as each other. No. You don't need to do that. So here's a technique, not just for this particular proof, but in general, if you want to show a whole bunch of things are equal to each other or equivalent to each other, you can use what I call a ring road proof. So here is a picture of a ring road proof. So what we do is we arrange these statements in our mind's eye, at least, in a ring, and we show that from each station in the ring, each place, like P is a subset of Q prime, we show that if that is true, then it follows that P difference Q equals P. Okay. And then we show if that is true, and so on. We arrange it right the way around in a ring. Think about why that does the job. So you can reflect on that. And we're going to have a chance, what we should, I think, as I recall, I've put on this week's practical sheet, don't panic, not the entire ring road proof, but just one little piece of it, just to give you a flavour. So, as I say, this entire proof is a bit of an imposition for you at this stage, but the general technique that when you want to prove a whole bunch of things are equal or equivalent, not just to do all possible pairs, but to do it in a ring, that's a technique that does crop up, and it's worth remembering. Okay, I'll unpack that in any more detail at the moment, we don't need it. All right, so why did I introduce this business of disjointness and subsettedness when we were supposedly in the middle of talking about set sizes? Well, because the whole business of set sizes is that things like set union, the sets overlap. So if elements occur in both sets, well, we don't want to count them twice. How are we going to organise that? Or set difference. Again, the sets might overlap. So we need to be careful that we get the counting right if we take the size of a set difference. But if we have the happy state of affairs that we know that our sets are disjoint, and this is, we've just seen one of the ways of expressing that, if Q is a subset of P complement, they're disjoint. There are no elements in common, there is no overlap. Well, in that case, the size of the union really is just the sum of the sizes of the two sets. So that makes life much more simple and pleasant. And now we see one reason why I picked out this way of expressing disjointness, because here is, in some sense, the opposite situation, that Q is a subset of P rather than P complement. And in this case, since every element in Q is also contained in P, when we take a Q-shaped bite out of P, we really do remove the number of elements that there are in the set Q. So in this case, the size of the difference, hash of the difference, really is just the simple subtraction of the size of P and take away the size of Q, which again, of course, makes our life pleasantly simple. Now, I've decided, in order to achieve the trick of bundling in that little bit of extra business from yesterday's lecture, I'm going to skip quickly over the proof of this result. I also want you to keep some resources of concentration, and the details of this proof might absorb quite a lot of those resources. So let me just point out that we use this little principle of partitioning. Here's the set and X is an element of P. Here's the set and X is not an element of P. So we use that principle, and then we use our little simplification rules, if you remember those, the axiom of membership. So the set of those elements X which belong to P, that's just a fancy way of saying the set P. So we use those two principles to show the first of the two laws I've just introduced to you, and indeed when we show the second of the two laws, again we use similar principles. Here's the being, and here's the axiom of membership getting used. So you can check the details for yourself. There's nothing fresh there. We're just using techniques and ideas that we've already seen. Where I do want to go, however, and pause a little more carefully, is that we might then wonder, so let me motivate us for a moment, just cover that out. We might then say, oh, well, that's very convenient in the case where we've got a union of sets, and we just happen to know that they don't overlap. Well, yes, that's all very straightforward. If we want the size of the whole thing, we just add the sizes. If only life were always like that. Well, there's what I call the union decomposition principle, which says that you can always rewrite any union using the union of disjoint sets. So let's see that. First of all, a little bit of notation. So this notation says, okay, I'm taking P union Q, and by the way, in case you haven't noticed, dear reader, P and Q are disjoint sets. So as I do so, the size of the result is just the sum of the two sizes. So that notation, yes, it's a union with a plus sitting inside it, means that. So it's a union, just as we already know it, but it's got this little extra advantageous property that what's more, it's a union of two sets which you are claiming, even as you do it, are disjoint sets. So it's immediate then, from what we've already seen, that when we take the size of a union of disjoint sets, it's just the size of the first set plus the size of the second set. Okay. So now, notice that any union can be expressed as the disjoint union of three pieces. So P union Q is always P difference Q, disjoint union P intersection Q, disjoint union Q difference P. So first of all, I will convince you that that is true, I hope, and secondly, I'll show you a picture. So why do we know this is true, and why are there three pieces? Well, I always like this theme. If you poke at any piece of mathematics, you dig down a bit, you come across fundamentals. And we're back at lecture 1 again. There are three pieces because there are 3 rows in the or truth table where you get the answer true. That's why there are 3 pieces, because this is an or on the left. Yeah? So if X belongs to P union Q, it passes the membership test, member of P, logical or member of Q. Okay? That is to say, if we use this shorthand, little p stands for X is a member of big P, and little q stands for X is a member of big Q, then we're back right down to lecture 1 again. P or Q, little q is true, and so we just look up the or truth table, and we can see that exactly one of these 3 things must be the case. So that's a logical justification of this decomposition. For those of you who like to think in pictures, here's the Venn diagram. There's the familiar picture at the top that we've seen before, with all the usual health warnings about the fact, of course, that might not always, that could be misleading. P or Q might be empty, one might be wholly contained inside the other, but this is a sort of diagram we might draw to help us just think about a common case at least. So there's P union Q, and we can see that it's got 3 parts in it. So we're just splitting up into those 3 parts and giving them each a name, and then we can see that they're all quite separate, they don't overlap, there's no confusion. So that is the union decomposition principle. We can always rewrite a union as a disjoint union, which is convenient for reasons that hopefully are clear. And this leads us by what might have been an unexpected route for those of you even who've done sets before, who've looked at the maths of sets before. If you've done that, almost certainly you will have been introduced to this sort of thing, which is the cardinality rule, which tells you about how the size of a union and the size of an intersection are related. Quite likely that you have been taught it, if you've seen it at all before, in the form where one or other of either the union or the intersection is on the left-hand side, and the other one is taken over on the right-hand side and subtracted. Well, of course, that's arithmetically equivalent. You just subtract one of these terms from either side.